All right, we're on 4.1. So let me just before we get into the problems here. So actually, I'll use this first question. So it says 6 of a bunch of weird symbols here. Okay. So this is just, there's some notation. There's a hump of notation you got to get over. It looks scary when you first see it, but it's actually asking a very simple question. So the question is, let's try to answer this one. Okay, so think for a couple seconds. Don't shout it out if you think you know it. Just give everyone a chance to think about this one. Or in English, it reads, the derivative of what would be 6x? So is there a function out there that if you took the derivative of it, you would end up with 6x as your answer? All right, so who thinks they know the answer? Anyone? A few? Rafe, you know it?
3x squared.
Okay, so that. Now, if anyone's feeling extremely savage, they could actually improve on this answer.
What? Plus some value.
Plus some value, exactly. So
Wow.
3x squared, everyone agrees that 3x squared has a derivative of 6x, right?
Yeah.
Okay. So then, but it's also true that if this expression inside here, you know, for example, 3x squared plus 1, or 3x squared plus 0, or 3x squared plus 17, or 3x squared plus 9 million, right? Those all have the same derivative. So when you're asking the question, what function or what expression or what function has a derivative of 6x, there's actually an infinite number of answers. The key part is, the key part is that, but then that could be any constant. So everyone understands what I mean by constant? Just a number, okay? So the answer to this then is 3x squared plus constant. All right, so C looked a little funky. How do you feel about that?
Yeah.
Make sense? Okay, so this is called some vocabulary. Let's get some vocab out of the way. This is this symbol is talking about an integral. So when you look at this as a whole, this expression, this is integral. Okay, so we might phrase this as the integral of 6x. You might read it like that. The dx just basically, for now, all we're going to think about is the dx just tells us that we are taking the integral with respect to x. Meaning this indicates that x is the variable in this case. Kind of like this dx tells us that, right? Take the derivative and x is like the symbol kind of we're working with. If you guys, yes.
So will there ever be a time where it's like in like 6x dy? Like will that ever be a thing?
Not in this class. That's a good question though. So if you take a multivariable calculus, you can start getting into things where you have the expression could have x's and y's and z's, and then you're taking the integral with respect to different variables, and it sounds scary, but once you work your way up to that, you're like, oh, it's actually not that hard. But yeah, for this class, for Calc 1, it's always going to be, there's only going to be one variable inside the integral, and then this symbol here is just going to tell you. Reading them is easy, but the only time you might get tripped up is if you are trying to write an integral and you make a mistake of say there's t's in here and you put an x there, that would be a mistake. Makes sense? Okay, the other way you might see this written is, so this could be the integral of 6x, or you could be saying, oh, this is talking about the antiderivative. Does it make sense why it's called an antiderivative? Hopefully, right? It's like, oh, the derivative of this is 6x, the antiderivative of 6x is this. Okay, so just a little back and forth there. So let's try to do this whole page. We'll get as far as we can with just trying to figure them out, and then we'll write we'll figure out a formula. So look at the next one, x cubed. what thing would have a derivative? So for the next one, just to clarify here, integral of x cubed. The answer to this question is like saying the derivative of what thing would give me a nice x cubed. Who thinks they got it? Dylan.
1/4 x to the 4th.
1/4 times x to the 4th plus any constant. Did you kind of start with the x to the 4th and then say, well, that would be 4x cubed, so I guess I could need like a little multiplier to take care of the constant, or sorry, to the coefficient. Are you okay with? How do you feel about that? Questiones? Okay. Why don't you guys try to figure out the next 6? Some of those are going to be a little bit more challenging than others, but just try your best. Take a couple minutes, and then we'll check our answers. See if anyone can get them all. Aight? And so don't let C throw you off. It's just why it happens to be your symbol that you're dealing with there. So if you see notation clarification, when you see this, this is really no different from seeing this. That makes sense? Or this.
Go there, man. I just made an oopsie, okay? I gotta adjust for my
No.
You get what I'm saying, right? The fact that in our culture we love this little crisscross symbol, it's just completely arbitrary. I mean, we could be dealing with anything.
I do appreciate the sheet.
Come back to you.
Yeah, don't worry. There's a couple on here that are going to be a little bit tricky to figure out, but we'll see if we can get them.
No. That would have been wise.
It's like lifting a long left. You don't know. I don't know if it's building tomorrow. Right?
No, oh, did I get it?
So then we just. Yeah, and then I get.
No, I didn't do it.
That, okay.
You just wrote it. Oh, I need to do this. I don't want.
This one, I can't think, it's got multiple levels, it's got layers.
It's got layers.
This.
This is equal C. Yep.
Oh, yeah. No, that makes sense.
Yeah. It was a,
Yes.
I can't, it's got multiple layers.
Here's our, if you're done, this is a nice little test to see if it's clicked in your head. If you can do all these in your head really fast, I'm not saying you should be able to do that yet, but if you can, that means you have figured out the pattern.
There's no pattern now.
Um,
I have no figure out
There's a
the
pattern?
No, exactly.
so let's look at, okay, who has an answer to C? What'd you get, Trey?
4y.
Oh.
Plus C. Everyone okay with that?
Yes.
Everyone heard what he said, right? 4y cubed plus C. Here's a little hint to think about. What mathematical operation is really tied in with taking derivatives? Multiplication. So what operation do you think goes with antiderivatives? Division. Okay, now D's a little tricky. What's the answer to D? Anyone? Alyssa? Very good. -1 over x plus c.
Ugh.
Okay. That one, it might not be clear where the division's happening, but it's happening. Oh, also, actually, I should say, let's go back to, when you take the derivative, right? The derivative involves multiplication, but also what other operation? Subtraction, right? Like, for example, when you take the derivative of, say, 3x to the 7, right? You go 7 times 3, mean number, okay? And then you also subtract 1, right? So this involves multiplication, and also subtraction. So the subtraction is happening to the exponent, and the multiplication is happening to the coefficient. And so when you reverse that, you know, what? What?
It's the heater's making a whiny noise.
Sorry.
You threatened it.
He felt itself in danger. He felt the danger.
There's some physics for you there. When I stand close to it, it like damps the vibration. So sometimes when I walk close, it'll stop, and then as I move away, it'll just keep going.
That's what happens with radios in my hand.
In your,
Like, you ever have it doing like the weird static and you like get your hand closer and it'll like clear up and then you take your hand away and then it'll go static.
on a radio?
Yeah,
That makes sense.
What kind of radio like that?
like a small radio.
Oh.
Okay, so so look what's happening there. So the derivative involves multiplication and subtraction, and then the integral involves addition to the exponent, and then division is involved. Like it's like the new exponent is dividing. So don't worry, we'll write the formula in a second. I just want to give you guys a chance to kind of you figure it out on your own. It's more fulfilling. E, what do we get?
I don't know. I thought I had it really good.
Trey, you got one?
-5 over x squared.
-5 over x squared plus c. Ever heard that?
I see it.
Okay.
That's easy.
F. F's a trick question. Well, it's not a trick question. It's so easy though. It tricks you. 4x plus c, right? What function has a derivative of 4? Well, 4x, right? Plus any constant. How about G?
5t squared minus 3t.
Plus.
Okay, so let me write that on the board just so in case. So it was 10t minus 3. That would raise a question. Oh, is this minus going to make things harder? Nope, not at all. It's just like when you take derivatives. If you have a thing plus a thing, does that make it harder? No. If you have a thing times a thing, does that make it harder?
Yes.
Big time, right? So the same thing will be true for integrals. If two things are being multiplied, it's much more challenging. So anyway, here you get 5t squared, all right, minus 3t plus some constant. Last one, h is the trickiest one. Rafe, you got it?
I think so.
Miss Vestal's out there. Hello, Miss Vestal. What'd you get, Rafe?
2/3 x to the 3/2 plus c.
Yes.
We agree.
I've been curved.
So if you didn't figure it out, you can still confirm, right, by looking at it that, yeah, 3/2 times 2/3 is 1. And then if you subtract 1 from my exponent, you get 1/2, which would give us the square root. Did you figure it out just kind of like reverse engineering it, or did you figure out
Yeah.
Like a formula, just kind
Well,
of reason it up.
If it's the 1/2, you just add 1 and then.
There you go. So that's basically how you figure out the pattern, which is, so he's like, well, yeah, if my integral, so this question was basically saying this, I'm always going to add 1 to my power, and then essentially figure out what number has to be there such that this times this would give me 1 in this case. So if you want a formula, it would be, say you had a times x to the n, where a is a constant. It's a multiplicative constant. Let's figure this out here. What happens to the exponent? We add 1 to it, and then you divide by that new number.
Yeah.
See?
I'm clicking.
You feel okay about that?
Line isn't so scary anymore.
Not so scary. So yeah, if you're still having trouble figuring out the pattern, there you go. That's a formula. You apply that formula a few times, you're gonna be like, oh, it's actually like not too tricky. So here, I'll run these real fast and just show you how this formula applies, and then we can.
Those are a lot of evaluations.
You think this is a lot?
I do think so.
I made bigly effort to trim this down as small as possible. Dude, do you know how many integrals that my calculus teacher made us do like every day? It was cruel and unusual punishment. Because you hit a point where you're like, okay, yes, I've mastered it. I know how to integrate these things. I don't have to do 50 every single day. She was a tyrant. Anyway, so this one would be, okay, it would be x to the 8th divided by 8 plus a constant. Or you might see that written, of course, as 1/8 x to the 8th plus a constant. Holla at me if you have a question, okay? This one would be, what's the new exponent?
6.
And then divide by 6, 3. Done. This one, new exponent of that dude would be 3, divide by 3. This guy, new exponent is 2, divide by 2. Forgot my plus C. Cool beans?
Get that thing.
This guy. New exponent would be 3, add 1 to the exponent, and then divide by 3.
Ooh.
New exponent here is 7. Scary 7, that's okay, you get 2 seconds.
That's okay.
False constant. Does that make sense?
Yeah.
Now, does this rule, does it only work if n is an integer? Spoiler alert, no.
Darn.
Look at Rafe's answer to this question. We know it's correct because we know how to take derivatives, and like, look, it follows the same rule, right? We added 1 to the exponent and then divided by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So there's only one scenario where this wouldn't work. Can anyone? There's one Bied value of n that it doesn't work for. -1. -1. Very good. Very good. So at this point, this will be. Yeah, we all see why -1's not going to work. Because you can't divide by 0, right? So this will be trivial knowledge for you for now, but it's kind of a fun fact. Because do you see how that's actually -1? This has a weird answer. It turns out to be the natural logarithm of the x. So,
Well,
like I said, for now you don't have to know that. We're going to cover that later.
be content with that.
What?
There's a handful of like funky results like this in calculus that you end up. We'll actually prove why that's true. It's actually a fairly simple thing to prove. Do it right now. Well, to prove it, you have to first understand that the derivative of e to the x is e to the x. We'll get to it. We'll get to it. So in a month or so, we're going to start talking about all like the derivatives of sine, cosine, tangent, e to the x, log of x, all those guys. Okay. Where were we here? So
2?
let's move on to 2. Let's do a couple examples from 2. So you're gonna find that like the trickier these get, the more you might want to rely on this formula. Not that you have to. If you have a good intuition for like reversing the derivative, then there's no harm in just kind of knowing the answer. But this is such a great formula because it works for anything that's either anything polynomial, anything of this form, anything where it's x to some exponent. Okay. All right. Let's apply it to let's do 2a. Well, we'll do all of them together. Is that it?
That sounds good.
So 2a is you have 4 over root x. So just like when you're doing derivatives, your first step is very often, I want to rewrite this expression in this kind of form, right? I want it to look like that. So I'm going to go, okay, this is really 4 times x to what power? Negative 1/2. Very good. So, okay. Let's go straight across. Okay, so we're going to be adding 1 to the exponent. So what's my new exponent? Positive 1/2. And what are we dividing by?
1/2.
Dividing by 1/2. So now it's disgusting, so I'm going to rewrite it as 8 root x. Any questions on that? No? Okay. Let's do B. So hopefully won't be too challenging since Rafe just told us this one. Same idea though. Let's say we're like, all right, well, 6 times x to the 1/2 power. We are going to be adding 1 to the exponent, 3 halves, and then you divide by that new exponent. So 6 divided by 3 halves. What is that? 4.
Yeah, I guess we have.
Don't forget. Most people, I'm just doing this so you can see the form being applied. Most people they jump straight to, they think of it, yeah, I'm dividing by 3 halves, but really I'm multiplying by 2/3. What's 2/3 of 6? It's 4. Okay, I don't know why I put C in there. I don't know what I was thinking. It's the exact same as 2a. Dumb.
Do you assume it's 6 root x?
Ooh.
Well done.
Woohoo!
D is a bit more, maybe slightly challenging. What are the raspberries for? You're going. What are you? Oh, okay.
How dare you?
Or not raspberry strawberries.
Okay. First step to this one would be, let's make sure we write it in a form that allows us to apply that rule. So this first term, I'm going to write it as 8 times x to the negative 3. And this term, I'm going to write it as 12 times x to the positive 1/2. So this first guy, I'm going to, a lot of mistakes get made in this step. You can see a lot of people would make it -4, right? That would be the mistake. If you add 1 to -3, it's -2 though. And then here, 3 halves, you can just add 1 to the exponent. We gotta simplify that because you can write that a lot nicer. How do you write this number, this expression?
4 over x.
4 over x squared. And here, 2/3 of 12 is 8.
Oh, yeah, no, that's right. I have my oopsies.
There you go. You might see that get written as, you know, the square root of x cubed, possibly, but. Okay, last thing I want to talk about, and then I'd like you to have at least 15 minutes to, 10 or 15 minutes to try to do it yourself. E and F. We will learn some tricky techniques down the road for dealing with, what if you have 2 expressions multiplied, and what if you have some expression squared or something, like how do you deal with that? Sadly, a lot of the time you just can't do much. But for E, who has an idea of what we're going to do for E?
Treat it as the same, like the whole entire thing as a number.
Wait, what'd you say?
I don't know, treat like the 2x plus 3 as one whole idea and then work from there.
We're going to get to that later. It's called U substitution. Yeah. In this case, it's going to be easier just to do what Trey said, which is just to multiply it out, and then we'll have 3 terms. Right?
Could you just do 2
It's,
Alright.
yeah.
Yeah, exactly. So soon, if you're looking ahead, we're going to call that, like Ave said, like you treat that as one little nougat. Yeah, we would call that U, and then it involves a substitution where you have to say, the tricky part is often, because if that's a U, this needs to be du for it to work. And so you end up with like a U and a U prime. We'll get to that pretty soon. It's actually on this problem set, it's towards the end.
Yay.
Yay, rejoice, rejoice. We get to do U substitution. Life is great. Okay, so anyway, it's like when we do derivatives. If you can just expand the thing and just get it into a sum of terms like this, that's usually the easiest way to do it. So let's square this. So 4x squared. That's it, right, guys? Right? Bad. Be it. That's J/K. Super funny joke. All right. We all okay with that?
Yeah.
We square the binomial. Now we say, oh, now it's just 3 separate terms that each term looks like that. So this term would give us the new exponent is, so why did I put an 8 there?
3.
That's 3.
3, so we gotta divide by 3, so we get 4/3 x cubed plus, well, it's x to the 1 power, so it's gonna be x to the 2 power, and then I gotta divide by 2, make it 6, and then 9 just gives me 9x. By the way, this actually conforms to that rule because it's 9 times x to the 0. So you add 1 to the 0 and divide by that, if you're wondering. Okay, are we all cool with that? That makes sense? All right, so F's very similar to that. F, you're like, we don't have a general rule for taking the antiderivative of a thing times a thing, so just expand that and then take the integral. Oakley dokley. Let's just keep it simple for now. That's all I want to cover for today. If I lost you, if you're just like, what the heck's going on, you can come talk to me right now. I'll try to help you work through it.